Right, this is our third video here about exponential growth and decay. We're going to do some more modeling today, starting with this wind energy problem. Uh, Take a second to read through the problem itself and kind of get an idea of what's going on here, and then we'll break things apart. I kind of skipped ahead and put the graph there for just ignore this for right now. We'll talk about that in a little bit. Read through the problem and see if you can come up with that model yourself. So remember when we set these up, we want the initial amount as our A value. So I'm going to be putting a 5 right here because they started at 5 gigawatt hours of energy in 1980. And the growth factor is going to be 1 plus the 0.59. That's the rate. So our growth factor, our base is going to be 1.59. Um, and I'm using t as my independent variable. You could also use x. I like using t for time. So since it said that this goes from 1980 and then for the next 15 years to 1995, we know that we want t to be 0 to 15. That actually is our applicable domain in this problem, and I have that written down here. Now the range, I know the smallest amount is 5, so I already have that there too. Um, and we'll figure out what that end value is right there in a second when t is 15. What I'd like you to do first is, and I have it in my calculator already over here, is go ahead and put that into your graphing calculator since we have to graph this thing anyways. Put it in as a function just like you type. There I have it in as y sub 1. And then what I'd like you to do is quit out of here, and instead of trying to play with the menu, excuse me, the Windows settings, I'm going to show you a little trick here to answer both this question right here and to get our ending range value. So what that is since I already have this in as y sub 1, I can use function notation and let, uh, for this example, or this question here, where it says in 1984 how much wind energy was there, we want t to equal 4 here. So I can use like function notation on my calculator and put in 4 for t into the function. I already have the function typed in, so all I need to do is tell it where to get it. So if you go to alpha and go to trace, remember alpha opens up all these windows here. Um, our function is in y sub 1, so I want to hit number 1. And then I'm going to put in parentheses like function notation, like saying f of 4. We're going to say y sub 1 of 4. And when I do that, it automatically puts it into that function. Sorry, I did it twice here. That's going to happen a lot here with my pen. So in 1984, we have about 31.96 gigawatt hours of energy. That is then how we're going to find our last value here for the range. So we know that the last value for t is 15. So we can do y sub 1 of 15. So I'm going to alpha trace. Actually, I'm going to show you something else here. If you don't have those fancy menus like some of the new calculators do, let me show you the old school way to get that y sub 1 here. You would go vars, and anybody can do this, even if you have the new calculators. Go to the variable button, which says vars, and then scroll over to y variables. We want a function, so hit enter on number 1. And then the very first one will be y sub 1, so you just hit enter. And it'll grab that y sub 1, just like the shortcut did before. And again, we want to put in parentheses whatever x value we're interested in, or in this case t, and that's 15. 1, 5. And when I hit enter, that tells me the y value at an x value of 15. So about 5,247 would be our ending range value, or applicable range there. So these are values that we could actually plot in order to graph this thing, because it does ask us to graph it, or I don't know if it actually, oh yeah, it does, it says right there, graph this model below. So we can put those 2 points on our graph, and then I picked a few other points here, and we'll talk about why I picked those points in a second. But what we want to do to start out is know that since this has to go from 0 to 15 on the x-axis, that we should scale that out appropriately. There's 30 lines in this graph that I gave you, so it goes perfect to make every line go by a half of a year. So every other line is 1 year. So notice the good job that we did here labeling this too. This is year since 1980. It doesn't just say time. Specifically, it is the year since 1980. And then we know that our y-axis has to go up to at least 5247. So since there was 30 lines, I decided 6,000 would be a good value to go up to on my graph. And I made every line then 200. Every 5 was 1,000. That got me up to that 6,000. Since 6,000 divided by 30 is 200, I went by 200s there. So, and then again, look at the labeling here. If you're asked to make a graph on the quiz, the test, even in your homework, do a good job of labeling things. Take time doing that. All right, so let's talk about then actually getting the graph. What you want to do is use your calculator to help you out. Use your calculator, get some table values to help graph. So we already got the function in. Okay, I'm not even going to end up looking at the graph at this to do this. I'm just going to go right to my table, second graph goes to your table, and I'm going to get some values off of here. I already have 0, 15, which, if you look at my graph, 0, 15 is like way down here. It doesn't really pay to plot anything there. So then I looked at it and said, well, look at these values here on the table are not changing very much. So I only decided to put the number 5 in, and then I went all the way and put 10, 11, and 12 in. So you can see those are the x values that we have there. At 5, we have about 81. I'm just going to round to the nearest whole number. At 10, we have 500 and about 16 or 17. 11, 821. And then 12, we had 1305 about. And we're just graphing this, doing a kind of as good of a graph as we can. These don't have to be perfect on here. So then I plotted those points. You can see them right there, 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 and there. And then I also have the 5,247 right there. Those are the points that I plotted. And then I just graphed the line. If you want to play around with the window, change your window around so that it kind of matches this one. Oops. You can do that. Our window goes from 0 to 15 on the x values. I'm just going to go by ones. And then the y values from 0 to 6,000. If you want to make it just like ours, you can make the y scale go by 200s like ours does. And when you graph it, should look a lot like ours does. Looks pretty nice. Then the next question asks, estimate the year when approximately 80 gigawatt hours of energy were generated. Well, we have a pretty good estimation right there. It's about year 5, or maybe even a little bit before year 5, since year 5 is 81. So let's put that function y equals 80 in, and I'm just going to do a little sketch here of what I'm doing. I know that my graph looks like this. I'm going to zoom out a little bit. Okay, there's my function. I'm going to put the line y equals 80 in. I'm going to find where those intersect. Looking for that point right there. Trying to find out what this x value is here, or value of t. Okay, so t, I'm just going to get from my graph calculator, but I do this to kind of show my work, to show what I did on my graphing calculator. So I'm going to go to y equals, and I'm going to put in another function, the one that I'm interested in finding that value of, and that's when uh, the gigawatt hours were 80. So I'm going to put in 80. I'm going to hit graph, and look at how, I mean, that's going to be really hard to deal with right there. So I'm going to zoom into that area. I'm going to go to my window, and I'm going to zoom into that area. I know that it's around 5, so I'm going to go from year 4 to year 6, and I'm going to, uh, since I'm looking for where it equals 80, I don't need to go all the way up to 6,000. How about we just go up to 100? So this graph's going to look radically different. I got to change my y scale too. I can't go by 200s if I'm only going up to 100. All right, so I'm going to do this to kind of zoom into where they're intersecting. So let's hit graph and see if that worked. Okay, so I got to go a little bit more to the right so I get a better view here. So I'm going to change my window to value of 8, an x value of 8. There, that's a little bit better. So I kind of zoomed into where that intersection was happening right there. All right, so now we're going to go second trace. We're going to find that intersection. Oh, look at how nice that is. Am I on the blue line? Yes. Am I on the red line? Yes. Take a guess. You're pretty much on it. So we're at 5.97, 5.98. So t is about 5.98. So, this is good to have as an answer, but if we were answering this in a little sentence, I would say, you know, at the end of 1985, almost 1986. because it asks for what year. So it's almost 6 years after, which would put it at just before 1986, or the end of 85. All right, so that was, not really outside the box of what we did yesterday, just another good example where we're using a graphing calculator. Okay, so now we're moving into something quite a bit different here. Yesterday we talked about uh, compounded interest, and the formula we had for that, I'm just going to write right here real quick, uh, was the amount in an account after a certain amount of time has gone by, t years to be specific, is found by taking the principal and multiplying it by 1 plus the rate that it's compounded divided by the number of times that it's compounded n taken to the n times t. Okay, so if we are going to compound, which means calculate the interest, monthly, that would mean that n is 12. Quarterly, n would be 4. Uh, Daily, n would be 365. Okay, so we used that to answer this question yesterday. So you can kind of read through that if you want. But when we went through that yesterday, when we were compounding monthly, where n equaled 12, we got an answer of $1,502.15. Putting $1,200 on 4.5% interest. Okay. All right. Now, what if we could compound constantly or continuously instead of monthly or daily? We're even going to go better than that. We're going to compound constantly. Now, that doesn't mean that there's constantly money being put in your account. I'm not sure, exactly when different banks or whatever would put that money in, but they're going to calculate that interest constantly. All right. Well, if you kind of were following along yesterday, the more you compound the interest, the more money you make. If everything else stays the same. So compounding continuously would help us make a little bit more money. Well, here's what I'm going to do. I'm just going to give you this formula for right now. And we're going to talk about where these things come from in a second. But this is what we want to use. As soon as you read the word continuously in the problem, you want to use this formula here. I call it the PERT formula. It's taking the principal, multiplying it by this value e, which we'll talk about where it comes from and what it is in a second. But just trust me right now, that there's a button on your calculator that represents that value e. All right, it's right here. I don't know if you can see where I'm at over by the calculator. So we're going to hit second and then this button next to the 4. Let me quit out of here real quick. All right, so here's what we're going to do to set this problem up. It says, what if this amount were compounded continuously? So that same amount that saved 1,200 compounded continuously. So we're going to go e to the r, so it's that same 0.045 times t. And t is 5 in this problem. So everything else remains the same, except now we're doing continuously instead of monthly. So here's what we're going to type in our calculator. We're going to go 1,200, and then we're going to put that e to the x. We're going to use that thing right there. So second, and then hit that button with that's an ln right there. We'll talk about what that means later too. And we're going to take that e to the 0.045 times 5 and hit enter. That's how much money we'll have after 5 years if it's compounded continuously. About $1,502.79. So we made a whopping, if you compare it to what we did before, we made a whopping 64 more cents by compounding continuously instead of just monthly. All right. And then I've got another example here. It's basically the same type of example. You can write this down if you want to. It's the same type of example, just different numbers. All right. You can type that in your calculator, see if you get the same thing. But now, I got one more example before we talk about what E actually is. All right. So then the next example says, what if you want to have after 6 years $10,000? Well, the formula we've been using is if it's compounded continuously, which this one says again, is PERT. Principal times that e taken to the RT. Well, this time we want to find p. So if we solve this for p, we would divide both sides by that e to the RT. So that's how we're going to find the principal here. So we know that we can find that principal by taking the amount that we want, which is 10,000, and dividing it by e to the, this time our interest rate is 0.056, and that is being multiplied by how many years? Oh, after 6 years. 6. All right, so let's find out what that is. 10,000 divided by, I didn't use my fraction, so I'm going to change this. I like using that fraction, so we're going to go alpha y equals 1. All right, so we had 10,000 over, I need to take e to the 0.056 times 6. So what that's saying is we would need to put in about $7,146. So let's just put that here. That's how much we would need to put in it initially. About $7,146 and about 23 cents. We'd probably want to actually round up, or even put more. And if you want $10,000 and make sure, you might want to put in $7,200 just to make sure you hit that $10,000. Although you're not touching anything, and if everything stays the same, the interest stays the same. If as long as you put this in, actually I would round up to the 4 to make sure. Otherwise you might be a cent or two short uh, after 6 years. But as long as everything stays the same, you're going to have that $10,000 in, maybe a penny or two extra now with the 4. All right, so what is E? Well, E comes from this idea right here, which hopefully that looks familiar. That is basically the piece of our uh, compounding interest formula, but I just got rid of the NT and the N, and I just put this value M right there. Because what we're doing is talking about compounding continuously. Well, if we're compounding continuously, that means we're compounding more and more and more. So we're looking for that M to approach infinity. That's going to approach infinity because that's what we're doing, is making it compound forever, constantly. And this is going to approach infinity because you're taking that massive number and just multiplying it by t. So it's also going to get really, really big. Well, picture what happens here. If m is approaching infinity, then this thing here is going to approach 0. I can spell. Man, I don't know why this thing is writing so poorly today. Maybe it's because I'm doing this in my car while I'm waiting for my daughter's soccer game to start here in Houston. Approaches 0. All right, that 1 over m does. I'm just going to do that. As m gets really, really big, that fraction approaches 0. But now remember, this is getting really big too. So we're taking 1 plus a really, really, really tiny number, which is just going to be just over 1, and taking it to a really, really big number. Well, if you do that, you end up getting the value of e. Well, here's what e is. If you want to know exactly what it is, or truncated, hit second and then e to the x so that we can get that e back on there again, and take it to the first. If you hit enter, there's what e is, 2.718. I'm just going to go to the thousands there. It's about 2.718. It's an irrational number, just like pi. All right? So it occurs a lot naturally in certain aspects in math, science. It's known as the natural number because of that. One of the cases that it pops up is in continuously compounded interest because of this idea right here as that value m gets bigger and bigger and bigger. So e is a lot like pi. All right. It goes on forever. It's an irrational number. And then this little thing here says you can simplify expressions involving e just like you would any variable, but it does have a value just like pi does. And it's an irrational number just like pi. Right? So that's what e is, 2.718 about, just like pi is about 3.14. We will do a little graphing with e. All right, so we need to know this idea, this function here, y equals a times e to the rx. So basically what we're doing is we're taking our y equals a times b to the x and saying, well, now our base is going to be actually this number e. Okay? But sometimes, actually, let me just leave this like this. But sometimes um, you can have natural decay too, because if you think about it, e is bigger than 1. So if we're just putting e right there, you might think, well, it's bigger than 1, so is this always going to be growth? No, that's where this r comes into play. We also have this value r being multiplied to x. If r is positive, then e will continue to be bigger than 1, and we'll have growth. But if R is negative, that'll flip that base, that E, and make it its reciprocal. And the reciprocal of E is, well, watch this. And just do this. We'll take that. We'll take 1 divided by that number up above. Actually, got a better way here. Just hit this button. It'll find the reciprocal of that last answer, which is E, and it's going to be about 0.4, about 0.3678. Okay, um, so that's what that base ends up becoming if R is a negative value. So in other words, if R is negative, then we have an exponential decay function. When you're graphing these, we'll actually just use our graph calculator to help us out with a lot of these graphs. We'll just go to the table and get some values. But I think this is a pretty useful thing to know too. When you are graphing it, these three values are pretty easy to find. We just said that the reciprocal of E, so if you put a -1 in for x, the reciprocal of E is about 0.4. If you put 0 in, obviously you get 1. And if you put 1 in, you get actually the value of E itself, which is about 2.718. So those are three good values to put on a graph, and then you can do any stretching, shifting that you want once you have those values in. All right, the last thing we're going to take a look at here is the idea of a half-life. Um, you've probably dealt with half-lives before. Pretty straightforward concept. It's a special type of decay where your decay factor is the same as your decay rate. They're 1/2. All right, so it's when you start with initial value and then whatever you have decreases by half every however many days or whatever the half-life is. So two different ways we want to look at this. That's why I have those two things there. We can either call this t divided by L as our exponent, where t is time and L is the length of the half-life. Or you could simply find the number of half-lives that have gone by and call it x. I mean, we could just use this idea right here. Okay, that might be a little bit confusing to start with, but I think once you see this example, it'll make sense. So you got this certain isotope here, or whatever it is, technetium 99M. I'm not even sure if that's real. I can't remember if I made this up or if I actually got this from the textbook or I will say it's legit. So this has a half-life of 6 hours. So every 6 hours, however much you started with, will decrease by a half of what it was. All right. So if you start with, well, let's say 100 milligrams, after 6 hours, you'll have 50 milligrams. After another 6 hours, then you'll be down to 25 milligrams, and then 12.5, and so on and so forth. So it says if there's an initial sample of 100 milligrams, write a function that models the amount of that stuff after X hours. So let's do this. Our model after X hours is going to be, actually, I'm going to call it after T hours to kind of match what, sorry about that, to match what we were doing up above. So after T hours, our model would be y equals 100. That's our initial amount times a half because we're talking about a half-life. Taken to the T, however many hours have gone by, divided by whatever the length of the half-life is, where our half-life length is, what was it again? A half-life of 6 hours. So T divided by 6. So now what I can do then is say, I can put in the number of hours and then know what the number of half-lives have gone by are. For example, it says how many or how much would be left after 18 hours. Well, for this one, isn't it really easy to know that after 18 hours, 3 half-lives have gone by? We can just use this guy here and just say 3 half-lives have gone by. So after 18 hours, I'll just do my work here. After 18 hours, I can just say, well, I know 18 hours means that 3 half-lives have gone by, so I'm just going to put a 3 right there. So I'm really using this concept right there. And basically throw it in my calculator, 100 to the, or times, excuse me, 0.5 to the third. And we get 12.5, which I actually said before. So there'd be about 12.5 milligrams left after 3 half-lives. Okay, so if you can easily tell how many half-lives have gone by, that's what you want to use, that idea right there. Even though I wrote my model differently over here, okay? Even though that's the actual model. I know how many half-lives have gone by, so I just put in that amount. For the other one, though, for the 20, what was it, 26 hours, it's hard to tell how many half-lives have gone by because 26 is not divisible by 6. So this is where you just want to use the idea of this first model, okay, or the one that we actually wrote that I can't see because my calculator's in the way. So we're taking 100 times a half to the t over 6, but time is 26 now, and the half-life is 6. So if I put this in, or you could figure out what that is as a decimal right away. That wouldn't be too hard either, and kind of go back to doing it the way that we did this one. But I'm just going to plug it in my calculator anyway. So 100 times zero point 0.5 to the, and then I'm just going to go 26 divided by 6, which is 4.96 milligrams. Okay, or like I said, you could have just found out what 26 divided by 6 was as a fraction or as a decimal, and then use that as an exponent on 1/2. So I'd take 100 times zero point 0.5 to the, and I'll just say second answer. It's, oops, whatever. I'm done with this calculator right now anyways. I think you know what I mean. Um, that is it for the exponential modeling. So we've got some things with financial applications, different exponential growth and decay, like the wind energy one that we did today, and some things with decay of value of like technology. I know we did yesterday. So we've got quite a few examples to look back at, and then the half-life stuff here too. And then what we're going to go into next in 7.4 is logarithms. So make sure you have this stuff, under control before you move into the logarithms, because understanding exponentials will help you understand the logarithmic functions even better.